Alright, welcome back to my YouTube channel. Today we'll be talking about plane waves in a good dielectric medium. So we have defined the dielectric medium. We have also defined our constitutive relations, which are these expressions. We must note this: for a good dielectric medium, the conductivity must always be far less than omega times epsilon. This is our Maxwell's equation in phasor form that we're going to be using. So let's go into the wave equation for E. We've derived this before from our conducting medium before, so we don't want to start deriving it from the beginning again. So if you don't understand how I did this derivation, you can go back to the conducting medium video I uploaded before this video to get a clue. So we want to just make a little approximation because we're talking about a dielectric medium, and our approximation is going to come from this expression here, this expression. So since we have our conductivity divided by omega epsilon r to be far less than 1, then this expression in mathematics should give us this. So know the difference between this and this. So we can find out by binomial expansion actually and apply the approximation. So let's go forward. So it means that this is going to be this. Then we have this expression at the end. So when we finish substituting this expression to be equal to this expression here inside our term for k is our complex wave number. We are going to have, when we expand this expression here, we are going to have this given as kr minus jki, of which our electric field propagating in the z direction can be given as this. Mind you, our electric field can be given as this, or it can also be given as e naught e to the power of negative propagation constant times z. So it depends. So we are not cramming it, we just know how to maneuver any way we are given the expression for the electric field. So our attenuation constant is going to be this term. So this is going to be our attenuation constant. So it is going to be from here, we'll do the comparison from here. Our ki is going to be our attenuation constant. Now our phase constant is going to be this, which is kr, and our intrinsic impedance should be this expression in this context of a good dielectric. So we have a problem in our MIS. We are given this problem to solve, so we are asked to calculate the following from this problem. So the first thing we want to see there is our intrinsic impedance. So this is going to be our formula. It's just a substitution we made here. So this is our formula for our intrinsic impedance. So when we do the substitution here, we are going to have this as our final answer. So this is our formula for our attenuation constant, this is our formula for our phase constant, and our propagation constant. Now if you notice, our propagation constant is equal to jk because this is what we are given in our electric field. This is our electric field we are given, and this is the electric field I worked with. So since this is the electric field I work with, my propagation constant can simply be just j multiplied by our complex wave number k. So these are propagation constant. So let's move on to our phase speed. Our phase speed is omega over phase constant. So it is kr in this case. So it's going to give us 6 times 10 to the power of 7. So our skin depth is just 1 divided by our attenuation constant. So it's going to give us that expression. So finally, electric field is given as this. So if this is our electric field, then don't forget this formula, that this is going to be the formula for our H field, which we can get. This is just a cross product. This is a cross product that we can look for at any time. So the cross product of, I think our A of Z is just going to cross A of X to give us A of Y here, our direction of the H field. Then if we substitute our intrinsic impedance and do a little bit of arithmetic